Hello viewers, welcome back to my channel. In today's video, we will discuss about electrical analogy of acoustic vibration. What we will do, আমরা different electrical এবং mechanical acoustic systems কে চয়েস করব, দেন আমরা তাদের different quantities কে compare করব এবং তাদের analogy কে আমরা find out করব. Before that, আপনারা যদি এখনো আমার চ্যানেলটি সাবস্ক্রাইব না করে থাকেন তাহলে ডু সাবস্ক্রাইব মাই চ্যানেল এবং আমার ভিডিওগুলো যদি আপনার ভালো লেগে থাকে তাহলে অবশ্যই লাইক এবং শেয়ার করে দেবেন অন্যদের সাথে। And if you want to join my online theory classes and also numerical problem solving classes, then you can contact me through the WhatsApp number and also the Instagram and Facebook. The details have been given in the background of my screen. So without wasting further time, let's start the class. So firstly, we will find out the analogy between oscillating LC system and oscillating block spring system. The electromagnetic oscillation of LC system can be compared with the mechanical oscillations of block spring system or a spring mass system. So this one is a spring mass system where a block of mass m is attached with a spring and it is moving along x-axis, along x direction, and a electrical LC system, that is inductance and capacitance connected in series, and an alternating voltage has been applied to this circuit, which is called the series LC circuit. So we will find out the analogy between these two electrical system and mechanical systems. Now starting with the spring mass system. For the spring mass system, the mechanical energy of a spring mass system contains kinetic energy and potential energy. Now the potential energy of the spring mass system is half kx square, where k is the spring constant, and kinetic energy would be half m into v square, where v is the velocity. So the total energy for the spring mass system would be E, which is equals to half m v square plus half k x square, or we can write it half m dx dt whole square plus half kx square, where v is velocity, which is equals to dx dt. Now if we differentiate this equation with respect to time, then we will get d dt equals to m dx dt plus d2x dt2 plus x into k into dx dt, as total energy is constant. So d dt would be 0, so right hand side will also be 0. From here we get dx dt into bracket m into d2x dt2 plus kx equals to 0. From here we get m d2x dt2, this term equals to 0. So we get this one, or d2x dt2 plus k by m x equals to 0, we take k by m equals to omega 0 square, which is a frequency. So we get d2x dt2 plus omega 0 square x equals to 0. We put it as equation number 1. So this is a second order differential equation of a spring mass system. So this one is a second order differential equation of motion of spring mass system. So its general solution would be x equals to xm into cos of omega t plus phi, where xm is maximum value of x, that is displacement. So the general solution would be xt equals to xm into cos of omega 0 t plus phi, where xm is the maximum value of displacement, omega 0 is the angular frequency, and phi is the phase constant. Now we will find out the electrical energy of LC system. So there are two forms of energy for this LC electrical system. One is electrical energy due to capacitor, and second one is magnetic energy due to inductor or inductance. So the total energy would be U, that would be for electrical energy of the capacitance, it would be Q square by 2C, where Q is the charge and C is the capacitance, plus magnetic energy due to the inductor, it would be half L I square. where Q is the charge in capacitor, C is the capacitance, L is the inductance, and I is the current. So similarly, we will find out rate of change of total energy, that is du dt for this electrical system. So du dt would be Q by C into dq dt, that means Q by C into dq dt plus L into I into di dt, or du dt which is equals to 0 as u is constant. So du dt would be 0, which will be equal to Q by C dq dt plus L into I means dq dt plus di dt means dq2 dt2, or we take dq dt common, in bracket it would be L d2q dt2 plus Q by C equals to 0, or L d2q dt2 plus Q by C would be 0. Or we can write d2q dt2 plus Q by LC equals to 0. Or we can write 1 by LC as omega 0, natural frequency for the LC system, and we can write d2q dt2 plus omega 0 square q equals to 0. So this is equation number 2. So this is also a second order differential equation. So its general solution would be Q, it would be capital Qm into cos of omega 0 t plus phi, where Qm is the maximum value of Qt, omega 0 is angular frequency which is equals to 1 by LC root under phi is the phase constant. So this is the charge. So if we want to find out the current, we will differentiate it with respect to t. So dq dt. So it will be, current would be minus of Qm into omega 0 into sine of omega 0 t plus phi. If we differentiate this equation, we will get current, or we can write it minus of Im into sine of omega 0 t plus phi, where Im is Qm into omega 0. Now in 2020 makaut btech physics question paper, a 2 marks question came as so that for LC circuit, charge Q undergoes a simple harmonic motion with time. So we have find out the charge Q here for LC system. This one is the expression for charge Q. So we can see from this equation that charge Q undergoes a simple harmonic motion with time. So the answer of the question has been solved. Now we will find out, or we will calculate the electrical and magnetic energy value for a LC system. So the electrical energy UE is Q square by 2C. So if we put the value of Q, we will get Qm square cos square omega t plus phi divided by 2C. The electrical energy would be UE, that is Q square by 2C. That means if we put the value of Q here, we will get Qm square by 2C into cos square of omega 0 t plus phi, this one. Next we will find out the magnetic energy, that is Qm, that is half of Li square. We have already found out the value of current. So if we put it here, we will get half of L into I square means, so this is the value of I. So if we put this value there, that is qm into omega 0 sine of omega 0 t plus phi, we will get omega 0 square into qm square into sine of or sine square of omega 0 t plus phi, or um equals to half L omega 0 means 1 by LC into qm square into sine square of omega 0 t plus phi. So L cancels out, so it will become qm square by 2c into sine square of omega 0 t plus phi, or the total energy would be U, that is UE plus UM would be this one plus this one. So if we add this, we will get qm square by 2c, as sine square of omega 0 t plus phi plus cos square of omega 0 t plus phi would be 1. So this is the total energy. Now if we plot this energy versus time, so energy along x-axis, so along x-axis it will be energy, along y-axis it would be time. So graph would be like this. So this dotted graph which starts from 1, it is for UE, that is electrical energy for the capacitance, and as its form is cos square term, so it will start from 1. Similarly, this line would represent UB, that is magnetic energy, UB or UM. So along y-axis that is UE or UM, along x-axis time. So this continuous graph is for magnetic energy, and the total energy would be constant, which is this value, that is q square by qm square divided by 2c. This is the total value, UE plus UM, total energy value. So this would be constant. Whenever the electrical energy is maximum, the magnetic energy becomes minimum. Similarly, whenever the magnetic energy is maximum, electrical energy becomes minimum, so that their sum of the total energy would become constant, which is equals to qm square by 2c. Now we will find out the analogy between electrical and mechanical quantities for this LC system and the spring mass system. We obtained the second order differential equation for the LC system, that is L into d2q dt2 plus q by LC equals to 0. For the spring mass system, the second order differential equation would be m into d2x dt2 plus k into dx k into x, which is equals to 0. So from these two equations, we can find the analogy for these two systems. So the first one is electrical system, second one spring mass system is the mechanical system. We compared both the systems and we find the analogy that for electrical system, charge is analogous to displacement of the mechanical system. Similarly, current I of the electrical system is analogous to velocity. Thirdly, inductance L is analogous to mass of the spring mass system, and reciprocal of the capacitance 1 by C, which is analogous to spring constant or the force constant of the system. Next, the electrical energy q square by 2c is analogous to the potential energy of the spring mass system. The magnetic energy of the LC system is analogous to kinetic energy of the spring mass system. Next, the electromagnetic energy, the total energy, that is U equals to q square by 2c plus half Li square, that is analogous to the mechanical energy of the spring mass system. And finally, the frequency of the natural frequency of the LC system, that is 1 by omega equals to 1 omega 0 equals to 1 by LC, that is analogous to frequency of the spring mass system, which is equals to root under K by M. So these quantities are of the electrical system are analogous to these quantities of the mechanical spring mass system. Next we will discuss about the analogy between forced vibration of a mechanical system with the forced voltage applied to an RLC system or RLC circuit. So this system is RLC system. Electromagnetic oscillation of the RLC system can be compared with the mechanical force vibration. So this one is the RLC system, that is resistance, inductance and capacitance are connected in series. So that's why it is called series RLC system, and it is AC alternating voltage or EMF has been applied to this circuit, that is Vt, V function of t. We will find the analogy between this RLC circuit system with a mechanical system under forced vibration. Now the equation of motion of forced vibration, equation of motion for the forced vibration is m d2x dt2 plus b into dx dt plus k into x equals to, suppose the external applied force is F cos of omega t. We take it as equation 1, where m is the mass of the system, x is the displacement, b is the damping coefficient, k is the spring constant or the force constant, and this one F cos omega t is the externally periodic applied force. So we have already discussed in my previous video of forced vibration that the mechanical impedance Zm is this expression omega m minus k by omega whole square plus b square. So the mechanical impedance for this forced vibration is denoted by Zm, which is equal to root under of omega m minus k by m whole square plus b square. Now for this RLC system, suppose an external EMF voltage is applied as E0 cos of omega t, which is the external EMF or the external voltage applied to this RLC system. So for the RLC system, the circuit EMF equation would be L into di dt plus R into I plus Q by C equals to that externally applied periodic EMF or voltage is 0 cos of omega t, where I is the current, L is the inductance, R is the resistance, Q is the charge and C is the capacitance, and E0 cos omega t is the external periodic voltage. We take it as equation 2. So we compare equation 1 and equation 2 and we find the analogy between different quantities. So charge becomes analogous to displacement, current I becomes analogous to velocity, inductance L becomes analogous to mass of the force vibrating system, resistance R is analogous to damping coefficient, reciprocal of 1 by C is analogous to force constant K, electrical energy Q square by 2C is analogous to potential energy half k x square. Now the electrical impedance, that is ZD, ZD is root under R square plus omega L minus 1 by omega C square. This is called electrical impedance. So electrical impedance is analogous to the mechanical impedance, that is Zm, that is 1 root under omega m minus k by m whole square plus b square. So this electrical impedance is analogous to mechanical impedance. Similarly, the reactance, this part of the electrical impedance is called reactance, that is omega L minus 1 by omega C, which is equals to the mechanical reactance, that is omega m minus k by omega. So these are the electrical reactance and mechanical reactance, which are analogous to each other. Next, resonant frequency is, or the natural frequency is omega 0, which is equals to 1 by root under LC. Similarly, in case of forced vibration, the frequency would be, natural frequency would be, or the resonant frequency would be root under k by m. These two are analogous. So these quantities of the electrical systems are analogous to all these quantities of the forced vibrating mechanical system. So in 2023, a 5 marks question came as, write down the differential equation of a series LCR circuit by an AC voltage, discuss a comparison between mechanical parameters and electrical parameters in relation to the oscillation. So you have to write down these differential equations 1 and 2. From there you have to write all these analogous quantities, and that would be the answer. We will find out the analogy between discharging series RLC circuit with damped vibration. This is the discharging series RLC circuit where L is the inductance, R is the resistance, and C is the capacitance. So this is the circuit for discharging series RLC system. That means after applying a voltage to the circuit and charging the capacitor, the voltage has been removed. For discharging circuit, the differential equation for the series RLC circuit would be L into d2q dt2, that means L into di dt, plus R into dq dt, plus q by C. As it is discharging, so right hand side would be 0. That means this second order differential equation would be homogeneous in nature. So for mechanical damped oscillation, the equation of motion is m into d2x dt2 plus b into dx dt plus kx equals to 0. This is equation 2. Now these two systems are analogous to each other. If we find the analogy, then we will find out that m is analogous to L, that is mass is analogous to inductance. Displacement in the mechanical system is analogous to charge of the electrical system. Damping factor B is analogous to resistance. Force constant K is analogous to reciprocal of the capacitance, and velocity is analogous to current. So these are the analogy for this series RLC circuit and mechanical damped oscillation. Now for underdamping condition or underdamping case, the motion would be oscillatory for case of damped vibration. So similarly for underdamping case, the RLC circuit will also show oscillatory decay. So for underdamping condition, root under a square minus omega 0 square is less than 0, where A equals to 2A equals to B by M for mechanical system, and omega 0 is the root under K by M for damped vibration mechanical system case. And solution for the displacement for the damped vibration, that is x equals to a to the power minus at cos of omega prime t minus phi, or a e to the power a means b by 2m into t into cos of omega prime t minus phi. All these expression for the underdamping vibration has been discussed in my previous video for damped vibration. The video link for the damped vibration part I will provide it in the description section of this video. Similarly, for the RLC series discharging circuit, we get the value of charge which is equals to Q0 e to the power of minus R by 2L into cosine of omega prime t minus phi, where omega prime is root under a square minus omega 0 square, which is equals to root under b by 2m square minus omega 0 square means k by m Similarly, in case of electrical RLC system, this omega prime would be root under B by 2m means B is analogous to R. So, R by and M is analogous to L. So, R by 2L square minus K is analogous to 1 by C and M is analogous to L. So, that would be 1 by LC. And the natural frequency, that is omega 0, is 1 by root under LC. So, this omega 0 is 1 by LC. So, omega 0 would be 1 by root under LC. This is the natural frequency. Now if we plot Q versus time graph for the capacitor for damped oscillator, it will be, the graph will be like this one. So, along a y axis we have plotted Q, and along x axis we have plotted time. So, this would be the equation for as an oscillatory motion. So, this is the graph for capacitor charge versus time for damped oscillation. In 2020 makaut btech physics question paper, 3 marks question came as write down the differential equation of a discharging series LCR circuit, identify the natural frequency of the circuit, under what condition will this circuit show oscillatory decay. So, all these answers I have discussed in this part. It says write down the differential equation of a discharging series LCR circuit. So, equation 1 is the differential equation for series LCR circuit under discharging condition. Next question was identify the natural frequency of the circuit, under what condition will this circuit show an oscillatory decay. So, for underdamped condition, the charge decay would be oscillatory in nature, and the natural frequency would be omega naught, which is equals to 1 by LC, this one. So, every part of this question has been answered. So, this is the last lecture of simple harmonic motion and oscillation under mechanics part of makaut btech physics syllabus paper code PH 101 or 201. Simple harmonic motion এবং oscillation এটাই হলো concluding video or concluding class. See you in the next video with a new chapter. Till then, bye.